Hi, and welcome to another Hopper languages video. This is about this feature in the languages that we're going to talk about today is the array. Hopper is a modern semicolon curly brace language similar to Java or C#, but without objects and designed to work well on small devices like microcontrollers and 8-bit microprocessors. Anyway, there's a few collection types in Hopper. There's lists, dictionaries, strings, and arrays. So these are things that can hold elements that you can iterate through. Arrays were implemented with some constraints to make them fast and small. So specifically for small devices. So I was first using them to do this benchmark. It's the 1980s Civ benchmark from Byte magazine. And it has an array of about 8,000 elements. And on a small device like my 6502 machine, I've only got 32K of RAM, and some of that's already used by the system. So using 8K of RAM, if you have 1 byte per element, is a bit much. So these arrays, they optimize if you use Booleans to use 1 bit per element. They're optimized in that it's one chunk of memory that's allocated and freed atomically. So let's run this quickly. I'm building it, compiling it. This is the editor, the Hopper IDE. It's written in Hopper. If I F5, it'll upload it onto the device. The screen at the top means we're in the debugger. At the bottom of the screen, we've successfully uploaded to my Raspberry Pi Pico. And then if I run this and then I Control C, because I'm not interested in the benchmark right now, I'm interested in the array. So here's the array down here. It's quite big, obviously, 8,000 elements. At this point, I can dump the memory. So I can dump the entire Hopper virtual machine memory in a structured way from the device, from the debugger. So let's do that. So it's getting this. This is the serial port connected to my Raspberry Pi Pico, and I'm going to dump my memory. My memory's been dumped. I'll exit, and then I'll have a look at that memory dump in the editor. So here's the memory dump that I got from the device. It's actually, the stack is like, this is the stack on the left here. It's like the live list of the garbage collector. And this thing with all the zeros and ones is the Boolean array. So flags array, and its total storage is about a K. So very efficient, both fast and small, especially when it's running on a 8-bit 6502. Right now I'm running it on a Raspberry Pi Pico. Memory for the entire program is just over a K, memory use by the virtual machine. So that was the justification for making arrays so that they can't grow at runtime. You can just create an array and use it. You can't make it bigger or smaller. And you can't store reference types in an array. You can only store value types in an array because it's it's garbage collected as one big atomic thing, not as the elements. So when you're thinking of a list or a dictionary, the elements are garbage collected individually. So you can put reference types in there. For example, a reference type could be a string. Okay, let's have a closer look at them. So let's do this. So that's how you define an array. The type, which is going to be a value type always, so usually an integral type. And I'm defining a constant. I'm initializing it to 4 elements. So if I compile that, it'll fail because it's expecting 5 bytes and there were 4. So if I add a 5th one there and now I compile it, I'm pressing F7 to compile. They're the shortcut keys on the menu here. So I compiled it. And now it's going to work. It's going to initialize that. I'm going to put it into a local variable, which is also 5-byte array. And then I'm going to call output, and it's going to, let's launch to the debugger. And so we'll put a breakpoint on here. Actually, I'm going to do this without optimization. Let's do that without the optimizer. So I'll do the same. I just, built it again, but without optimization, just to make sure my breakpoints work properly. They usually do, but sometimes they get confused by optimization. So F5. So I'm running on my microcontroller. This is my serial port connection to my microcontroller. And I'm about to step in. I put a breakpoint on output. So now I'm going to F11 to step into my breakpoint. And it's going to, for each through data, which is an array. So it can iterate it through it this way. And it's going to, I should have just stepped over that, but it stepped right in. So let's do that. Let's just, so we're iterating through. And the other way you can do is you can ask the array for its size, for its count. And you can see the output over here in the serial port coming back from the device. All this code that we're looking at right now is running on my device. I'm debugging remotely from Windows. So now I'm just iterating through it with a regular for loop rather than a for each loop. Okay, so it's not terribly convenient to have a hard-coded size like this. So, like, because if I add a sixth one here, it's not going to compile. So you can do an empty array like that. So that means it'll infer the size from whatever you're assigning into it. But it's a conscious decision to do this. So the intent's visible and obvious. So if I do this again and I compile, now if you look at the bottom of the screen, the error's at a different location. So if I double click on the error, why am I not going to the error? Huh. Byte local, it's over here. I don't know why that double click didn't work to jump there. Oh, it did. It did jump there. Let's try that again. Don't know why I'm not jumping to my error. Should be able to double click on the error message and jump to it. But anyway, I've got the line number. So line 25. I shall have to check that. So now it's saying I'm trying to assign a variable length array into which is currently 0, 1, 2, 3, 4, 5 elements long. Let's make it 5 just to make it clear. And I can't 0, 1, 2, 3, 4, 5, 6. So it's 6 elements long. I'm trying to assign it into an array that's got 5 width of 5, size of 5. So that won't work. So if I do that, my error should move. That's better. It's jumping through the error. I must find out why that other one didn't jump. So now it's saying there's no overload for this function that matches, because I'm trying to pass in one that has an indeterminate size into this. So if I change that and build, now it'll run. There, it ran fine. Okay. So what's going on here? So you can't over constrain, but you can under constrain. So what you can do is you can do it the other way around. So I could do something like, because I know this is 6 elements long, I could make that 6, and that'll work. Because it's at runtime, it knows that's 6. It's putting that in there. It's 6, and it's a size of 6, and then it's calling output, which is a method that's been written to handle any length array, and that'll work. And so it might be slightly confusing. Basically, you can't over constrain in the assignment. But you can do the opposite. So you can assign something that's less constrained to something that's more constrained to something that's less constrained. And what it does, the reason to keep this is because you may intend your array to be a specific size. Like if it's a 4x4 matrix or a 3x3 matrix, you're going to want it to be a fixed size. And if it's not that size, it would be an error. So there is a benefit to having fixed size arrays. Anyway, I think that's all I got to say about arrays. You can see how you can make them from constants, initializing them from constants. I think you can just initialize it inline as well. So you could just do this as well, I believe. I think that should work. Yes, so that works too. As you would expect it to. Yeah, I think that's enough about arrays. Thank you for watching, and I'll put a link to the rest of the language playlist in the end credits.